Let's put all of the individual components to regression together and actually do a regression from start to finish. The first step in doing any regression is to look at the data using a scatter plot to see if visually it looks like your two variables are linearly associated. If it appears that the two variables are linearly associated, then calculate the correlation coefficient R, which measures the strength and the direction of the linear association. If, based on your scatter plot and the correlation coefficient, it appears that there is a linear relationship or association between your two variables, go ahead and do least squared regression and get your least squared regression equation. Once you have your model, you have to assess it to see whether it is a good model or not. Two components to this are the R-squared value and the residual plot. Remember, even if you have a good R-squared value, if your residual plot is not good, in other words, there is a pattern in your residual plot, you probably should not use that model as modeling the association between your two variables. Once you assess the model, if you say you have a good model, then you want to go ahead and interpret your slope coefficient. You can use your model for prediction purposes. And the last step is you can do various inferences on your regression equation. You can test a significance about the slope coefficient. You can do inference on your predicted y values. So let's go through the regression process for the following data. We have relative humidity in percent and heat index in degrees Fahrenheit. This is the relative humidity and heat index in an environment whose actual temperature is 85 degrees Fahrenheit. We want to see whether we can use the relative humidity to predict the heat index in an environment that is 85 degrees Fahrenheit. We want to do least squared regression for this data set. The very first step is to do a scatter plot. To do the scatter plot, make sure your data is in lists. We have our X data, or the relative humidity, in list 1. We have our Y response data in list 2. That is our heat index. To do the scatter plot, let's go to second stat plot. Plot number 1, here's scatter plot. We want to look at the scatter plot of relative humidity versus the heat index. So we need to change the resid to list 2. Zoom 9 gives us our scatter plot. Does it appear that the data is relatively linearly associated? Yeah, looks that way. So our scatter plot of our data is complete. Now we want to calculate the correlation coefficient. To do that on the calculator, we actually have to run the least squared regression. So let's do that. Stat, over to Calc, number 8, linear regression with the model A plus BX. We put our X data into list 1, our Y data into list 2, and if we do comma, vars over to Y vars, 1 for function and Y1. This will do the linear regression and it will store the regression equation in Y1. So let's do the regression. We were looking for the correlation coefficient. We see that the correlation coefficient is 0.975. So there is a strong positive linear association between relative humidity and heat index. The third step is to get our least squared regression equation, our regression equation. That we have right here when we did our least squared regression to find our correlation coefficient. We have that the predicted heat index is equal to 75.95 plus 0.277 times the relative humidity. The next step is to assess whether we have a good linear model or not. We want to calculate the R-squared value and look at a residual plot. Our R-squared value is given to us because we had our diagnostics turned on when we ran the least squared regression. We see that our R-squared value is 0.951. This means that 95.1% of the variability in heat index, our response variable, is explained by our model of heat index hat equals 75.95 plus 0.277 times the relative humidity. Now let's look at the residual plot. That is a scatter plot of the residuals versus the X data used to construct the model. If we go to second stat plot, plot number 1, we want the X data to be our X-axis. We want the residuals to be our Y-axis. So we need to change L2 to our residuals. Every time we do a regression, the calculator stores our residuals. So let's go find the residuals. Second list, go down to the R's and we see residual. Hit enter. Now we are going to do a scatter plot of the residual versus our X data. Zoom 9. There is our residual plot. We do not have a good residual plot. There is a pattern in our residual plots. We underestimate for small values of relative humidity and large values of relative humidity. For relative humidity in the middle, we overestimate. We probably should not use this as our model to model the relationship between relative humidity and heat index. Let's just carry out the remaining steps for regression, assuming that we have a good model. The fifth step is to interpret the slope coefficient. We see that our slope coefficient is 0.277. What does that mean? It means that for every 1% increase in relative humidity, the heat index increases by 0.277 degrees. Our slope coefficient is 0.277. That means that for every 1% increase in relative humidity, the heat index increases by 0.277 degrees Fahrenheit. Let's use our regression equation to predict some heat indexes. First, we want to predict the heat index at a relative humidity of 32%. We need to plug 32% in for a relative humidity. So our predicted heat index will be 75.95 plus 0.277 times 32. That gives us a predicted heat index of 84.8 degrees. Now let's predict the heat index at a relative humidity of 76%. The predicted heat index will be 75.95 plus 0.277 times 76. What is that value? That value is 97.0 degrees Fahrenheit. So, if you were in a room whose actual temperature was 85 degrees Fahrenheit, the relative humidity was 76%, it would feel like the room was 97 degrees Fahrenheit. The last step in the regression process, which we're not going to do in this example, is inference. We can do inference on the slope coefficient, beta. We can do inference on the predicted values, y hat.